This is the last presentation of today. We still have a quarter, but I think I'll exceed a bit the time. And this is about Model 3, the site investigation, and about the conceptual site model. So the content of the presentation is the objective of this session. Then I have a remark when you deal with contaminated sites. Then I present you the table of contents of Model 3. Then I have some examples of POPs contaminated sites, examples of site components of POP contaminated sites, the task and deliverables of phase 1, the preliminary site investigation. Then for the preliminary site investigation, I have made a process flowchart to understand the process. Then I will go into a bit more details on the gap analysis and then a summary of task and deliverables of phase 1 and 2 and the process flowchart of phase number 2. So this is what we're dealing with, the first 2 phases of the contaminated site management. The objective of this session: explain the content of model number 3, site investigation, assessment and conceptual site model, highlight that contaminated site management is a multidisciplinary activity, explain the task and deliverables phase 1 and the same for phase 2. So this is the objective of this session. Dealing with contaminated sites, and I will slowly read this because it's important, and it's written by Mr. Frank Swatjes, which is an authority on contaminated site management in the Netherlands and working for the Ministry of Environment. And he says, when you have a wide scientific knowledge concerning contaminated fate and transport, processes in soil and groundwater, site characterization, human health risk assessment, ecological risk assessment, and groundwater related risk assessment, and have experience with designing cost-effective remediation solutions, and you have a creative personality, and have a good communication skill, and are in the position to take policy decisions, go ahead. Otherwise, build a team. And that's what I said earlier. If you enter into the contaminated site management, you cannot do it alone. You have to build a team with all the different kinds of expertise involved. Table of content of Model 3 is after introduction. I go to phase 1, and then the phase 1 elaborates on the objective and task, and then we go into details on desktop study, the site visit, reconnaissance survey, the initial conceptual site model, and the reporting. And I would direct you to paragraph 2.6 of this guidance because it provides you with a format how to report the results of the phase number 1. Then the next section in this module is phase number 2, detailed site investigation, exactly the same, this objective and task. And here we have the text which elaborates on gap analysis and site investigation plan. The gap analysis gives you the input to make a site investigation plan. So what you do not know is being listed, and then that leads to your sampling and analysis plan. Then I will go into details on the field investigations, data interpretation, the detailed conceptual site model. And here again, also in the last section, we give a format for reporting the collected information. And also this module ends with reference, and this reference gives you the opportunity to be informed by reading all the documents here. So this is a large list of documents which can be consulted to get more information on the different subjects. Examples of POPs contaminated sites. This is a storage of Lindane production site in Turkey, and here is a storage facility completely filled with waste of the Lindane production. We did this assessment and now this is cleaned already, but the soil around it is still contaminated and needs to be surveyed. This is a contaminated site of an ACO distribution center in Tajikistan. Many sites in the former Soviet, they have many ACO distribution sites, especially in the cotton producing region, and they are contaminated. Here again, such a site in Azerbaijan. This is a DDT contaminated army site in Vietnam. This is on the Ho Chi Minh Trail in the remote area where they were using DDT to combat the malaria, and after the war it was left behind, and so it was source of contamination for the people hunting and the people living around and for the ecosystem. This is a bunker filled with POPs pesticides in Vietnam, and we assumed that this bunker was leaking, so we expect the soil to be contaminated in and around, including the groundwater. This is a PCB contaminated site in Serbia. In these storages, they have stored PCB containing equipment, and it leaked, so the site was contaminated. This is an acetar lagoon in Romania, a large refinery. Here is the refinery, and these are the acetar depots contaminating the groundwater around this facility. This is a PCB industrial site in Montenegro. This was an aluminum melter where they had a workshop where they were repairing transformers and condensers. And this activity polluted the soil around this storage facility with PCB. This is again a former agricultural distribution center in Azerbaijan, this one, and this is another one here in Azerbaijan also, close to the railroad station. I showed you the different sites, and this is illustrating question of the different cats. Yes, there are many different types of contaminated sites in many different situations. So each site needs a site-specific approach. But such sites are contaminated, and they are composed of site components. And a site component can be stocks with hazardous waste. This is an example of a hazardous waste in North Macedonia. And here, these drums of hazardous waste are in the open air. And this is an irrigation system to cool because they were by sunlight or by sun being heated, and they exploded, so they need to be cooled. And this was a very bad situation, causing a lot of problems, contamination into the groundwater. You see here the water standing, and that all leached into the soil. Fortunately, this is being removed now. This is in Ujar. This is in Azerbaijan, and this is a former contaminated, former storage facility for pesticides. And you see here all stained floors and walls, all soaked with pesticides. This is the same site, but now outside. And outside here, these patches of contaminated soil due to runoff from the demolished, from other demolished facilities, storage facilities. Here is an example of contaminated sediments at the same site. Because there were contaminants on site, due to runoff, the contaminants migrated through this channel outside the site. This is the hotspot of one of the hotspots. The buildings were collapsed while they still had obsolete and POPs pesticides stored, and due to weather conditions, runoff, sunlight, all degraded and all migrated into the surrounding, including in the groundwater. And there was a vegetable garden close to this facility. So here the groundwater was tested, and it turned out to be contaminated. And we restricted site use of this. We restricted the use of the groundwater for irrigation because it was contaminated. So these are the site components of a contaminated site in general: stocks, buildings, soil, sediments, hotspots, and groundwater. Task and deliverables phase 1, the preliminary site investigation. Deliverables are initial conceptual site model and a preliminary risk assessment. And this is being discussed in a separate model number 4. The tasks are desktop study, collect all available site information as much as possible, site walkover, visit the site, interview stakeholders, make a photo report, and check the site information. And then a reconnaissance survey, take few samples to verify assumption. And the Swift site assessment is a terminology used to make an initial conceptual site model and carry out your first risk assessment. Desktop study, collect all available site information and baseline information. Baseline information means information of the soil, for instance, and you want to know what the baseline is. So what is the quality of the soil outside this site where it's, and the site which is not influenced by the activity on site. So you know what it should be. But information is, for instance, Google Earth reports and maps, geohydrological reports and maps, land use planning reports, geotechnical information, cadastre or land registers, archives of the ministry, archives of the company, and so on and so on. And here in this text box, nowadays it's very cheap to carry out a drone flight. And with a drone flight, you can get point cloud, meaning a dense collection of points with X, Y, Z coordinates. And with that, you can make a digital train model. And by making overlapping area photographs, you can make a site orthophoto map. This is nowadays a tool which is easy. Let's say companies should do this, and it gives you a lot of information, and it gives you a detailed site location map. Here, this is an example of such a map. And the earlier you make such an orthophoto map, the better it is, because you will make use of it during the whole process of site management. Site visit to interview people living around. I have a questionnaire, but this is a standard questionnaire I use, but you can make your own standard checklist for site interviews. You need to meet former and the present site management to get information. A site walkover, meaning you visit the site, take enough time to visit the site, and try to get workers with you to explain what is on site, where they have dumped waste, where the processes are. So you make notes on the installations on the site. But besides the site itself, you also visit the surrounding. You make a site location map and you update. If you have an orthophoto map, you update your orthophoto map with information collected on site, facilities, function of buildings, where underground tanks are, and so on. And you make a site photo report. And all the data collected should be recorded to be used to construct the conceptual site model. So this is information, and this is the task you have to do for a site visit. Site photo report. I want to go into a bit more details. You make photographs of the potential sources of contamination, the potential receptors, source receptor pathway, and the potential receptors. So meaning the source can be a tank, the source can be a waste pit, the source receptor pathway can be wind, can be running water, can be erosion, and the potential receptors are the workers on site, the birds, the cows entering the site, children playing on site, dogs on site, the surroundings. You make photographs of the surroundings. What is the land use of surrounding area? The entrance road. You already take photographs of how to approach the site. The buildings, subsoil infrastructure. Are the signs of subsoil infrastructure such as tanks and installation on site, etc. And this illustrates that the photo camera you use should be robust and possible to clean. This is a photo report of the Ujar site, and this is the photo report of the potential sources. Potential source 1, remains of pesticides on an old floor. The walls and the roofs are collapsed, so this is a source. Contaminated floors inside the former DDT, floors and walls. This is a source. Here again, remains of pesticide on the floor, and this is dumped contaminated rubble from the side wall. They have demolished the wall, and the wall had the foundation of the wall was impacted by the contaminant, and they were not aware of that, so they dumped all the waste, including contaminant waste, outside the site, creating a lot of more contamination, and this will enlarge enormously the remediation. So that's, you be aware before you do any actions on the site, be aware of the situation to avoid unnecessary remediation costs, because this is now all contaminated. And if they had known before, they had separated during demolition, clean and contaminated rubble. These are pictures of source receptor pathway infiltration. Rainwater on the site infiltrates into the soil at the hotspots. Surface water in the drainage, I explained further, runoff takes contaminated soil particles, and here in this drainage, this takes care of the migration. Runoff through flush hole, this is very specific. They have constructed new wall, but they did not, let's say, compacted the soil very well. So at non-compacted locations, due to excessive rainwater, flush holes under the foundation of the wall took care of the migration of contaminants, soil particles. And here surface drainage went outside the site, so on the public area. So this is also a pathway far away from the site itself. These are the receptors, people working on site, surface water in the drainage, cattle, and here the groundwater. These are the receptors. And this is how you make a photo report.
And this picture is just illustrating that the fact that you, before you do any inventory of any investigation, you should be aware and you should be make an agreement of what your site is that you are going to survey, and that you're sure you are covering the impacted land or not. And in this case, it was a bit difficult, and I'll show you on this left-hand side on the picture. The green line was the complete former agro distribution center, and the inside of the blue line was the affected area. So with the aid of this area photograph, we made this map, and the map has, of course, a north arrow, a scale, and then a legend. And here you have the areas as being identified. The impacted area, and here was also the patch of impacted area. Outside was some rubble. We made a cross section A1 and A accent, and here B accent. The old railway lines. So this gives you already an impression. Yes, okay. This slide shows you the importance of making an agreement with your commissioner, with the one who is giving you the order to do the investigation, of what to investigate. Be aware before you start any investigation what your survey area is and where you have the authority to visit. So it's important. And use maps to indicate the survey area with everybody involved. The case of which was in Azerbaijan, it was really a question, because the green line is the line of the border of the former agro distribution center. The blue line is the line where the pesticides were stored and where we have visible impacted soil. With the information from the area photograph and the site visit, we made a soil map or a map of the site as part of the conceptual site model. And this map has a north arrow, a a scale, and of course a legend. And in the legend, we have divided in various land uses and various observations. For instance, these red dots are visibly impacted soil, and also here then this one is commercial area, this is residential area, and this was fallow land, and here we had some rubble dumped. So this map gives you a short overview or an easy overview of what is going on. The yellow line is a cross section, and the blue line is also a cross section, which we have constructed to give an impression of the subsoil. Then we go to the cross section, A accent. This is the impacted soil, and here you have source, secondary source, receptor pathway, and the receptors. And this cross section gives you an idea of what you could expect in the soil, and you have identified the receptors, the source receptor pathways, and the receptors. Here indicated with the R, the environment, people living around the source, impacted soil, secondary source, the contaminated soil, in the subsoil, and here the groundwater. As we already have discussed the gap analysis, here the gaps are indicated with numbers, and these numbers are the things you do not know and you want to survey. Another thing on the cross-section here, this is the scale, and this is a simple visualization of your initial conceptual site model, one of the deliverables of phase 1. Okay, these are photos from the photo report, and the photo report should have photos of the potential sources. This is another example from another country in South America. These are stockpiles. This is a stockpile of top pesticide, and this is a potential source of contamination. This is buried, burned, empty packaging of top pesticides, so a potential source. And this is an airstrip, an agro airstrip. This was a rice farm, and they used spray planes to put pesticides and fertilizers on their rice. And this is the rinsing place of the spraying plane. So the spraying planes were stationed here and then were cleaned. And the cleaning water, the rinsing water, was just flushed off the place. And you see here the impacted soil due to the washing. Okay, this is a cross section as part of the initial conceptual site model. Here you have the storage facility on this photograph. Here it is. We expect this is the source, the stockpile. This is the buried pesticide, and we expect that rainwater infiltrates into this buried pesticides, and infiltrated rainwater enters the soil, enters the waste, and flushes contaminants. So we probably have a plume. The same inside the store. We think that the pesticides are leaking. They enter the groundwater, they go with the groundwater flow, form a plume, and they may enter surface water in the drainages. Here the sources are the buried pesticides, the stockpiles, and the receptors are the environment and the rice fields, because they use the groundwater which may be contaminated. So a simple illustration of my understanding of the situation. This is the part where the planes were rinsed or washed. So planes were stationary here after being used to spray. The pesticides were flushed off. They enter the soil. That's a hotspot because it was pure pesticide entering the soil. They form contaminated soil. They most probably have entered the groundwater, and they move towards the surface water. So simple source receptor pathways, receptors. And here dust taking off by wind. So the source is the soil, pathway is the wind, and then of course it enters the environment. Simple presentation of my understanding of the current situation as part of the initial conceptual site model of a site. Another example of a photo report. Here, photos of the entrance. Here you already anticipate on the remediation. You already take photographs of the accessibility of a site. This is easy. Here you can enter with trucks, so no restrictions on that. The surrounding. Within the surrounding was a factory growing cannabis for medical purposes. So people are working here and may be impacted by, for instance, wind that carries contaminant particles. Here, the surrounding public road is nearby, and the on-site shoe factory. There was a factory just close to a dump site with chemical waste. So this is how you make a photo report. This is a photo report of the sources. This is the depot with mundane production waste. These are the remains of a chlor process plant. Mercury contamination was expected. This is the other source on the site, which is a stockpile of drums. And these are remains of tanks with unknown fluids. And I expect that these are also sources of contamination. This is a detailed photograph of the soil around the chloralkali plant, and by scraping of the soil we saw small droplets of mercury in the topsoil. Here you see them. So what we expected was true. This site was also contaminated by mercury. Then photos of the receptor pathway on the same site, rainwater runoff and broken sewer system spreading into the soil and subsoil. So the pathway is the runoff. It enters the sewer is broken, so the soil around the sewer is most likely contaminated. Another pathway, infiltration of percolating rainwater in the dumped waste into subsoil. This dumped waste here was not covered, and so rainwater infiltrates through the waste and may have entered the subsoil. And then of course there was runoff here. You see that signs of leakage of waste, and so infiltration of rainwater from the surrounding soil also. And here infiltration of rainwater and spraying water of this drum storage facility. These photographs gives you already an impression of what is happening on site. And this photograph gives a lot of information to the reader of your report of the preliminary site survey. Here the receptors, animal, pet and pets roaming around on site, the workers in the shoe factory, the ecosystem illustrated by the birds on the roof, and the ecosystem illustrated by the vegetation on site. So receptors are animals roaming on site, people working on site, and the ecosystem. This is the complete survey site, scale, north arrow, and this site is far larger than the site I just demonstrated. Here is the blue area. I will give you some details about it. And this is the initial conceptual site model of an Ockersley dam production site in North Macedonia. And here this is made based on my understanding of the situation on site. And here you see the dump sites, the drum facility, the other dump sites, the shoe factory, the former HCA plant, the electrolysis plant with mercury, here the drops of mercury, the sewer, infiltration, expected contaminated sediment in the surface water. We expect to have an aquitine down, and all the question marks are illustrating my gaps in the understanding of the on-site situation related to the contaminants. And the contaminants are mercury, TPH, volatile organic carbons, and HCH, alpha, beta was dumped here, and DNAPLs. Here a DNAPL is formed by components that are heavier than water and they accumulate on aquitines. And here this TPH, which is lighter than water, forms an LNAPL, so a floating layer on the groundwater level. And this is the groundwater level. Any questions on this initial conceptual site model made with only my information collected by site visits, interviews, study of archives, and my experience? And this initial conceptual site model goes with the report. And the report, the format for reporting initial conceptual site model is given in the guidance and goes together with this picture. This picture tells you, of course, the on-site situation, but more details are presented in a report. Any questions?
I don't see any hand raised.
Okay.
I don't see any comment.
Okay.
But please feel free, any of the participants, to ask questions on the questions and answers on the chat or to raise the hand whenever you want. And after, if you have some other questions, we can share with you the contact email from Goodwin, and you can ask directly to him also after if you want. So please feel free. And now, Goodwin, the floor is yours.
Yeah. Yesterday, I promised you to give you a bit more information on the reconnaissance survey as part of the preliminary site investigation. And to be short, if you see this white heap on your site, this may be pesticides, but this may be also fertilizer. It makes a huge difference in cost and risk if this is pesticides. If this is pesticides, you have a few extra tons of pesticides, which you do not expect it. So you want to know what it is. Also related to the health and safety and to your budgeting. Because if this is pesticide, you need around $2,000 per ton. If it is fertilizer, you can just bring it to a dump site or even use it. So it's very convenient if you know what this is in an early stage of your survey for budgeting purposes, health and safety aspects, and investigation efforts. So it's very easy that you take a representative soil sample of this depot, bring it to the lab, and ask what it is. You can even do it on site, because if it is a pesticide, it does not dissolve in water, and if it is a fertilizer, it dissolves in water. So also with simple tests, you may already tell what it is. But please only carry out simple tests by consultation of chemists. And if you are in a country or in a situation where you have such questions, and that it is, let's say, for instance, benzoic acid, a chemical which is used in the food industry, you may develop your own tests In this case, it was benzoic acid, and we developed a test, a field test, to detect if this is benzoic acid. And that saves a lot of cost. Another question, what is in this bunker? If this bunker is completely filled with pure pesticides, or is this bunker filled with pure contaminated soil? Makes a huge difference in cost. So what we did, we just drilled through this concrete, we took a sample, and we find out that it was filled with contaminated soil, so less costly than when it was filled with pure pesticide. So this is my reconnaissance survey, taking 1 or 2 representative soil samples or samples from waste, analyze them, and then react or confirm your assumption, and inform the people responsible for budgeting and health and safety what is in these depots and in this bunker. Yes, I will continue. The other deliverable of phase 1 is the preliminary risk assessment, also called tier 1 risk assessment. A risk has 7 origins, and we now focus on the environmental risks. And the environmental risks are human health risk, ecological risk, and migration risk. And as this is a very important aspect of your site assessment, model 4 is solely covering the environmental risk assessment. So in the model I'm discussing now, it's not given. There's a special model for environmental risk assessment, which is model 4. Now, this is a picture of the strategy of a preliminary site investigation. As I said, there are pictures, satellite images available on the internet, but it's very advantageous if you have the financial capability to already carry out in this phase a remote sensing by drone, and then you can record a point cloud and you have a nice date site location map. If you have this, you can continue, study reports, visit the site, study archives, and with all the information, you make an initial conceptual site model. The information of the initial conceptual site model will give you source, receptor pathways, and then you can do the first level 1 risk assessment. You put everything in report. This is your deliverable with your deliverables, and this report is the input of your next phase. But to go from preliminary site investigation to the detailed site investigation, you have to bridge all the gaps. So the gap analysis is your bridge to the next phase. This is a flow diagram of the process. You start your phase 1. Is there a report available? Yes. Does it cover all the issues? Yes. Are there risks? No. Or is the risk assessment available? No. Perform a risk assessment. Are there risks present? No. Finalize. Yes. Continue. Now, and if it is this one, this road, perform a risk assessment, perform the investigation, make a conceptual site model, carry out a first level risk assessment, are there risks? Yes, and then proceed. So if you carry out a phase 1, this helps you with the process. Any questions? This diagram is given in the report, and the report can be downloaded from the website of the Stockholm Convention. Gap analysis, the initial conceptual site model. Gap analysis is the bridge between phase 1 and phase 2. And phase 1 is the preliminary site investigation, and phase 2 is the detailed site investigation. 3 questions. What do we have to know to complete the conceptual site model? So what is missing? What do I not know? And the other questions? What do we have to know to design the site cleanup or remediation? You already start in this phase thinking about remediation and collect information about the access road, connect information about the surroundings, and then the last question, what type of survey or assessment do we need to fill the gaps? The detailed site investigation has to confirm or react, and when confirmed, characterize all potential sources, potential source receptor pathways, and potential receptors identified, all in phase 1. So the detailed investigation is looking for the confirmation or reaction of your potential source receptor pathways and potential receptors. Then we come to the plan of the detailed site investigation. And the plan, depending of course on the site components, but here we have the 4 site components: stocks with hazardous waste or pesticides, contaminated building, buried waste, and the contaminated soil and groundwater, including the source area. To know what stocks of hazardous waste, we have an inventory plan, the inventory of the hazardous waste stocks, meaning you start to count, start making pictures, reading labels to see what is inside and what is the quality. Contaminated building is a building assessment plan. Assess the contaminated parts of the building. The buried hazardous waste, the waste pits, is a pit survey plan. And contaminated soil is a soil and groundwater sampling analysis plan. And here again, assess vertical and horizontal extent defined for the source, the same for the soil, and the same for the groundwater. So gap analysis for the initial conceptual site model for stockpiles, bulk pesticides. What type of survey we need? We need an inventory. The question, what do we have to know to complete the conceptual site model? The source, the type of pesticides, the amount, the state of the packaging, source receptors, pathway, condition of the floor of the building, condition of the roof of the building, condition of the wall. And the receptors, accessibility of the building, the use of the building, and are soil and groundwater contaminated, yes or no? I would like to draw your attention to the accessibility and the use of the building. If there are obsolete pesticides in the store, it should be not accessible for anyone. It should be locked to prevent contact with it, with the waste. Then the question, what do we have to know to design the site remediation? The repackaging budget. Here, already now, you have to know what is the budget available for the repackaging, future storage building use, and in-country available disposal techniques. Here also, you already look forward and collect as much as possible information for the remediation. In this inventory plan of stockpiles, you also have your basic information, address, contact details, accessibility of the area. Can I come there with trucks? The needed material and capacity, dus PPA, personal protective equipment, manpower and their qualifications, sampling material, equipment, and a detailed planning and time. But besides that, you need a skilled map with a north arrow, location of the stocks with hazardous waste, and then field forms. Logbook, inventory field forms, and sample transport forms. And I here direct you to the FAO environmental management toolkit of the FAO. You can download it from the internet, and in the guidelines is a link to it. And here the FAO has extensive guidance on stockpile inventory. And this is a summary of the inventory plan, knowledge gaps, information about the amount and type, hazardous waste, and the waste used. So you have to know what was and what is in the store. Now, investigation, consult site administrator, consult management, review land register, past transportation and storage operation, etc., etc. Be aware of HSA site regulations. Worst case scenario, selecting your PPE. So when you go to the site, you go with your worst case scenario, select your personal protective equipment. You conduct your inventory, make site location map, and make a photo report. And what human resources? In this case, you need at least 3 people: team leader, a worker, and a watch. And I said a watch because if you go inside a storage facility, pesticide storage facility, you need to carry PPE, personal protective equipment, but there should always be one outside watching and observing you and be able to contact you or to call for help when something goes wrong. Now, equipment and collaboration agency, site location map, filled in questionnaire of the interviews you have had, contact with the community authorities, stationary, again, personal protective equipment, your photo camera. You have to collaborate with land survey contractors, if any, to make a map, sampling equipment, field forms, sample transport, and logbook. So this is a summary of what should be in your inventory plan. And I've made this also for the other site components. This is a report as part of the preliminary site investigation with stockpile. Now again, photos taken, but on a map you take where the photos are taken, you indicate the direction of the photos. So photo 1 is taken from here, photo 3 is taken from the outside, photo 4 is taken from here. So in this way you can easily share your information with your reader. Scale, north arrow, the number of your store, site visit, plan, date, the name of the drawer. So that's also important that you write down who has made this map. In case of question, you can contact him. This is the gap analysis of the initial conceptual site model of a contaminated building. And again, here I will not go into much details, but the questions: what type of survey, what do we have to know to complete the conceptual site model, here source receptor pathway receptors, and questions: what do we have to know to design the site remediation of the building? Again here, budget, the construction, the sub and above service facility like water, pipe and electricity, the future use of the building and the site, and the in-country availability techniques and facilities to clean the rubble or to dump the rubble. So this is a picture of the contaminated building, and here again a summary. And I will share with you this presentation. You can consult it later on, but it is more or less the same. Here again, the human resources, 3 people, watch, operator, and here photo camera and so on. So this is more or less the same, but I give this because for every type of survey, for every component, you make a site investigation plan in this case a building assessment plan, with this information, because you have to direct your field crew to carry out, and it's important that they have all their equipment and material with them for such survey. Here is it also for the building. You make a drawing and a photo report with a North arrow and the scale, the photos inside, the material, and this is the building itself. Then we come to the initial conceptual side of the waste pit and the gap analysis. So what type of survey for a pit? It's a pit survey. Questions here are more or less the same. The source, do I need to know? The source receptor pathways and the receptors. And here the questions, what do we have to know to design the site remediation? And we talk about now, this is the pit. So what we do not know is the influence. We do not know the depth of the pit, but we also do not know the influence on the sub-surveys and the surveys of the practice. As you can remember, this pit was filled with waste from pesticide packaging, and they burned that years after years. So this is also the question marks which we do not know. We do not know how deep this is. We do not know the groundwater depth, and we do not know if infiltration has affected the subsoil and the groundwater. So this is my gap analysis. We do not know if there's a top cover. This is the pit survey plan. In the first instance, we thought it was a square, and we decided to install the following boreholes around to verify the quality of the soil around and to see if the vertical extent was correct. Here also closer to the boundary, and then one inside. This was the plan, and we decided to do the survey in a raster. As the pit is small, we took a raster of 2 by 2 meter. So this is the expected location of the buried pesticides. This is the raster, the north, and the scale. And this is the legend. Boreholes for mapping horizontal direction surveys, boreholes for mapping in the horizontal direction and the surveys, and boreholes for the vertical. And this is the last one we install because this is, of course, the most contaminated part. This is more or less the same. This is a summary of the pit survey plan and summary, knowledge gaps, investigation efforts, human resources, and equipment. And I will only discuss the equipment and collaboration. And here you see drilling equipment, drill rig or manual auger, extension rods, foil for cuttings, sample containers, measurement equipment to make a map, and here field forms, and here this is an important aspect, bore log. Now, if you install a borehole, you always have to describe your soil profile, and you do that on the standardized bore logs, and later I will give you an example of such standardized bore log. As we discussed the plan here, I give you already information of the carried out waste pit survey, and here you see now what at the end it was different than we expected, and far more boreholes are installed to map. So your survey plan should also have the flexibility to install more boreholes because the situation is never, let's say, as you expect. And here are the bore logs with the legends: undisturbed, disturbed, undisturbed, subsoil, and pesticides. And here this is then borehole 17, and that around the pit was around 2 meters, and the groundwater was also seen at 2 meters. So they have been digging a pit until they reach the groundwater, and they have been filling it. So this is just after you have carried out the phase 2. This is another survey, but it's far larger. This was in Armenia, a large dump site of POPs pesticides, and here you see on this hand, you see the map, my bore logs, my equipment used, manual with a hammer to bring down the GOG auger. We use GOG auger, and here you see the pure pesticides, whitish and blue, and the top cover. We collect everything in a bucket and not laying it around, and put it in a separate place to not, let's say, spread chemicals on the surveys due to the exercise. Now this picture is taken especially to demonstrate you that when you do pit surveys or any survey, you have to know the wind direction, and if you stand upwind, so in the direction of where the wind is coming from, you have not the risk of being exposed to dust coming from your bore cuttings. So therefore this wind sock is installed to know where you have to stand. So to know where you have to stand when you are examining your soil cuttings. And here is my colleague, half face mask, helmet, gloves, Tyvek, boots. This is the result of the pit survey carried out in confirmation with the plan, but we found out that the cap they installed was not correct because they did not know that there was another pit, and this is outside the cap. So we found out that it was a cap. This is the pure pesticides, the red one, and the yellow one is the contaminated soil. Here we come to the gap analysis of the soil and groundwater. Same questions, but now you want to know the extent in horizontal and in vertical direction. I take the example from the rinsing plane, from the spraying planes. So these are the questions. You remember? But now I want to know the extent in vertical and horizontal direction. And then I do want to know the groundwater depth and if the groundwater is impacted by the leaching. This is sampling as an analysis plan for contaminated soil, and here it's an example of a hotspot survey. Again, a scaled map with the north arrow, expected location of the source area, the proposed soil and groundwater locations, necessary field forms, logbook, bore logs, sample transfer form, number of soil and groundwater samples to be taken for analysis. So this was the plan. Pesticide store. These were signs of spills on the surface. This was a drainage. So to get the boundaries of the impacted soil in vertical direction and horizontal direction, we took now here composite soil samples. Composite soil samples is a way to minimize costs. If you bring every individual sample to the lab, it's costly. So we decided to make a conceptual site model, a composite soil sample taken 2 to 3 meters outside my visual boundaries of the impacted soil. And we decided to take this side, the north side, and here the south, and here also the southwest side. Composite soil samples are soil sampling method which saves you cost, but when you have elevated levels, you have to get to know where the elevation is, and then you have to sample or to analyze the individuals. So when there is no elevation here, then you may assume that it's clean. When you have elevation in the composite soil sample, you take each individual sample and then you find out where the elevation is. This is the mapping of the contours of a hotspot. Okay, now here is the summary of a survey plan for contaminated soil and groundwater, and here the equipment, drilling equipment, again the bore logs. I see you have a typo here. That's one. I promise you to give you an example of a bore log, and on a bore log information to be collected are project number, project title, the drilling order number or ID of the observation, name of the foreman driller, date of execution, the location of the observation on the sketch and preferably also the coordinates, the depth of the bottom of the various soil layers or soil horizons, the texture of the various layers, the details on various layers including estimated in quantity. So you may see gravel, you may see waste, you may see organic matter, so you estimate the content of your soil horizon, then the ID of your sample and the sampling section, and if you use on-site measurements, PID, photo ionization detection, XRF from heavy metals, MIPS and ROSTs. I will come to that later. These are all detection equipment on site. Groundwater level, results of the use of oil detection pen and other organic lab observation. An oil detection pen is very simple. It's just a small quantity of water in a small bowl, and then you drop a small piece of soil in the water, and then you may detect oil. Other organic lab observations are also visually observations, the color, but also the smell. But don't use that purposely, because you may then be exposed to contaminants. And of course, you write down the boring system, including the use of lost casing, and lost casing is explained later. Additional information on the bore logs for monitoring. If you install a well, also this information has to be on your bore log. Each well has a label, material and configuration of what is the protection of the wellhead, added quantity of working water. If you install a well, you need working water. The electric conductivity measured in the working water, the clean, you have to pump your well clean, so you record the amount you took away from the depth of the filter bottom, expressed in centimeters below groundwater, and then the groundwater electric conductivity. Now we go to such bore logs. This is the bore log, a standardized form. This is the one I use. So the top part is the information on the project number, project code, location code, profile, region, town, street, the client, the company, the driller foreman, the logger, type of observation. It's a bore log or it's a pit. The method, we use the hand auger. No, we use the machine-driven piston auger or whatever. The dimension of the observation point, it was a pit from 1 meter by 1 meter and it was 1 meter deep, or it was a borehole of 2 meters deep and with a diameter of 10 centimeters. The location, and here I direct you to a footnote, and the footnote said, provide a sketch of the location of this observation point at the backside of this borehole. So every individual observation point should be recorded on a small sketch at the back of your borehole. That makes it very easy to see where the borehole is taken for later to make your site location map. And it gives you information when someone wants to go to this specific point. Then the bottom part of this general information is about the groundwater. This groundwater depth, groundwater yes or no installed, filter sock around the well, water used to install, water used to develop, the seal type, did we use bentonite, the seal depth, the filter types and the filter depth, the total depth, the filter depths, diameter, and the protection. And this is my horizontal description. So horizon 1, the depth is from 0. Here you put the bottom of the depth of your horizon, and this is the sampling. So if the top layer is, let's say, 50 centimeters, you put here 50. If the next layer is again 50 centimeters, you put here 1 meter. The sample is taken from, for instance, from top soil from 10 to 20. So you put here 10 and you put here 20. So let me do the example. So the top layer is 50 and I took a sample from 10 to 20, and the code often goes together with this project number, let's say 1, and the project code is L from Libya, and the location is A. So the code could be then, and you make together before you go, you make appointments how this coding is done so that it is, so Libya, it's a site, it is the borehole number 1, and this is then sample 1. So from Libya, from site A, project, the number of the borehole is 1, and then the sample is 1. So if you do the next one, 180 to 100, it's LA1, 2. Now, texture, sand, organic matter, 1%, soil color, dark brown, remarks, waste of packaging. So this is the way how you make a bore log. Is that clear? Okay. So I will have to share now again. Now we come to the task of soil and groundwater survey, the importance of the scale of your initial conceptual site model, and also of course of the conceptual site model. It makes a huge difference if this is 50 or 500 meters, and it makes a huge difference in your efforts if this is 2 meter or 20 meter. So please, if you make any map or any cross sections, give the scale, because the scale determines the details of the site investigation, but also, of course, the cost. If you decide to take a raster of 2 by 2 meters and the scale is not given, you may come to excessive costs. So the scale is a very important aspect, and before you start any investigation, discuss what scale you are going to use. Pit survey is, of course, another scale than a large groundwater plume. Large scale, 1 to 10, 1 to 100. Small scale, 1 to 10,000. Task of the soil and groundwater survey: consider soil and groundwater mapping. Work with a flexible work plan. So you may come across unexpected things, so you should be flexible in time and flexible with your resources. So have enough material with you, have enough financial resources to extend your survey with 1 or 2 days. The mapping team includes a soil technician and other experts available during the field work, meaning that if you come across difficulties related to groundwater, you should be able to consult someone who is specialist on groundwater survey. The decision-making process is well defined, so it should be clear if the field crew can decide themselves to extend or to replace borehole location. And therefore, decision-making power should be in the field, to not, let's say, use time to consult by telephone to the one giving the decision. The decision-making power should be in the field. That's very efficient. Then again, mapping scale and the mapping details agreed upon. In most cases, plus or minus 10 meters for soil, plus or minus 10 meters for 20 meters for groundwater. That's a rule, but it depends completely on the size of the expected soil and groundwater. But this is more or less in average. Soil and groundwater characteristics will tell the migration potential, the maximum depth of soil profiler influence, and the maximum depth of the groundwater influence. And information on the contaminants of concern allow to identify tracer or indicators of presence of contaminants, meaning that you may have a broad spectrum of contaminants of concern, but some are more mobile than others, and some are cheaper to be analyzed than others. So select a tracer or indicator which is cost effective and which gives you the correct extent in horizontal and vertical contamination. So if you have a mobile component expected in your groundwater, then you can use this mobile contaminant like benzene, for instance, or toluene as a tracer, and that saves you costs on the chemical analysis in the lab. This is a slide on a mapping method which also is cost saving. You can use a grid, for instance, 15 by 15 meters. So if you use a grid of 15 by 15 meters, your soil boundary can be here or can be here. So it's plus or minus 15 meters. So you continue, and finally you, by taking samples, you know that this one was contaminated, this one was not. So somewhere in between is the boundary. So in this case, I put it in the middle. So it's minus 7.5 or plus 7.5. This is with the grid, but you can also decide to do a dynamic sampling plan, meaning you install a borehole, number one, when you are pretty sure that it's clean. Then you install a borehole where you're pretty sure it's contaminated. And then you install a borehole just in the middle, and this one is clean, and this one is clean, and this one's contaminated. So you have the same result, but you have one borehole less. So if you have to do this on all the sides of the expected spot of contamination, it saves you cost and time. But be aware that normally the sequence of installing boreholes is from expected clean to expected contaminated to avoid cross-contamination. Here you deviate from this rule. That means that you have to clean in between your borehole very good your equipment, or use other equipment, an extra set. But cleaning your equipment from one borehole to the other borehole is important to avoid cross-contamination. Is this clear? Oh, okay. So sampling in the grid and sampling with a dynamic sampling plan. Okay. Baseline sampling of the different survey areas. I already mentioned this baseline sampling, and baseline sampling is actually the sampling of area which are not influenced by the activities that causes a contamination. And that is to know what the original soil quality is. So in this case, we had taken 3 sampling areas, one in the forest, one in an agriculture field, and one in the sediment of a drainage, outside the radius of influence of the contaminant. So this was upstream, this was somewhere outside the deposited dump, which was in the forest, and there was also a pit with waste in agricultural land. And this sample should be analyzed on the same components as your contaminants, and this gives you the information on the background values and the values of the original soil, and may be used as remediation target values. Also, you take photographs while you do the soil and groundwater survey to give you information. And the top one is an illustration that you always need to have some scale on the photograph to know what you're looking at. Because if you only take a photograph with this man, you think it's around 170, 180. But this is my friend in Vietnam who's very small. But I know that this auger is 120, so the profile is around 2 meters. Here, drilling my soil cuttings, details of the soil cutting, wells, every well should have a number, drilling in the hotspots. This was a survey site in St. Petersburg in Russia, where you have a large leakage of an underground storage tanks of fuel. Here is the profile, and you see it was highly disturbed by human influence. Here, old layers, and here finally you come into the soil, and here is your measuring tape. My bore logs. Here a detail of the profile, and here sampling groundwater, my cooling box to take the samples under a cold chain to the laboratory, my labels, and now after taking it goes immediately into this box with ice packs and brought to the lab. Soil sampling, here a basket with, this is in Vietnam, a basket with my equipment and my bore logs and other forms. They used a tray to collect the soil cuttings and to describe and to take the samples. Here, gas mask, protective boots, trouser, and your sample should always be on a tray which is clean, or here this is a piece of a banana tree, and this was clean, so here the sample is. And this is my soil sample. The label on top here, LH13. So task soil survey. Here is a cross section after the phase 2 is carried out, and here you see the very detailed information on this cross section. This was an impermeable layer being interrupted. Here was my contaminated groundwater, and here is the groundwater under the clean soil layer, and we found out because here this borehole 628 was taken, and then we say, hey, it's clean, but we continue through this layer, and then we saw that at the bottom of this layer were some traces of contaminants, and that made us to proceed and drilling, and then we found out that this layer was intercepted and that under the aquitar was a plume. So in this case, this cross-section illustrates the situation. This was in Poland and the result of contamination by a paint factory. This is another cross-section based on a very detailed survey, and here is the strategy of such phase 2 survey, a detailed site investigation. Gap analysis, you remember that I demonstrate you the strategy from the phase 1. Here comes it. Here's the bridge, the gap analysis. The gap analysis gives you the detailed investigation plan, the tables I just showed you of the different site components, but you also need permits, cost estimates, quality control and quality assurance plan, health and safety plan. Then you come to the sampling, the samples, labels, ready for transport, cold chain transport, sample analysis to the lab. And here you have your geographic information system, your digital train model, DTM, made with the information of my drone flights in phase 1, because that gives you a point cloud, and with the point cloud you can make a DTM. I showed you this example. This was made with a point cloud, and here you see my DTM. Then the reporting contains map, cross-section, photo report, analytical certificates, and with the information you make your next level of risk assessment, and all goes into a phase 2 report. And this is the input for the phase number 3, the site remediation assessment. This is more or less the sequence or the strategy for a site investigation. And you may, of course, differ, but this element should be there. So sampling analysis plan, the field work, the sampling, cold chain transport to the laboratory, information is put into a GIS, Geographic Information System. You update your conceptual site model, photo report, analytical certificate, maps and cross-sections, risk assessment, and all goes into a report. And the model provides the format of such report. And the report is the input of the next phase. This is a picture or an infographic of the 2 phases. Phase 1, the preliminary site investigation, desktop study, site visit, reconnaissance survey, remember, sampling of huge amounts which may be riskful in the next phase. Swift site assessment, meaning you make your initial conceptual site model and your first risk assessment. And then the stockpiles, contaminated building, buried pesticides, soil and groundwater contaminated, detailed site investigation, inventory of stocks, building assessment, pit survey, and soil and groundwater and source area survey. And the deliverables of this phase 2 are gap analysis, site investigation plan, updated conceptual site model, and tier 1 or tier 3 risk assessment. And here is a flow diagram of the steps to be followed for phase 2. And here the question is gap analysis and initial conceptual site model. Phase 2 detailed investigation when present. Yes. Phase 2 report available. No. Perform detailed site investigation and update your initial conceptual site model to a conceptual site model. Perform your risk assessment. Risks are all assessed. Are there risks? There are no risks. Exit. Yes, there are risks. Are they acceptable? Yes, they are acceptable. No. Proceed to phase 3. And you can, of course, walk through it by giving the yes or no questions. It's a guidance to help you in the different steps to be taken for a phase 2. This is also available in the module. Thank you very much. This was the presentation on the investigation, the phase 1 and phase 2. I will now go to my next presentation. Okay. Let's say radical mitigation measures is the question on waste and on polluted soil. Now, I know from medical waste is often being incinerated, and the incineration of medical waste is often done on hospitals itself, but it needs to have incinerated with do not, let's say, produce dioxin, because a lot of plastics and other chemicals are being burned and the risk of forming dioxin is large. There are guidance documents on the internet of constructing such small incinerators, but it's not my field concerning the contamination of soil by medical waste or other waste. I think that is discussed just in the presentation before. You have the hotspots, the waste pits, and then the remediation of a waste pit is, of course, excavation, and then bring this to an incinerator or any other technique. And the techniques to treat waste is presented in the Basel Convention. And in our guidelines, we have a special model devoted to the techniques for site remediation. So I will come to that. That's model 5. Yes? Does it answer the question?
I think you were very clear, but we will wait the feedback. It's clear, Almadi.
Okay. This presentation is about the soil survey equipment. So we discussed the site investigation, and the site investigation concerns, of course, soil sampling, and therefore I have this presentation made with a summary of what is needed to carry out a soil and groundwater survey. So smart start, know what you measure. So you have to know before you start, you have to know what you want to do. And I will discuss the aim of the fieldwork engineering equipment, the principle of sampling, and what do we need to know. So there's a Dutch saying, meten is weten, to measure is to know. And combined with a Latin saying, scientitia potentia est, knowledge is power, tell us, if you measure, we know, if we know, we can act correctly. This presentation is made together with a company called Eikelkamp, and this company is a Dutch company, and they are the suppliers of all kind of survey equipment, and they do have agency all around the world. Soil and groundwater survey equipment, the aim of the field engineering equipment, research and sampling of soil above the groundwater, and above the groundwater is also called VEDIS zone or unsaturated zone, the soil and groundwater below the groundwater or saturated zone, and the sediments below surface water. That is being discussed, and that these are the samples which are often taken to characterize the soil and groundwater contamination. The central question in environmental soil and groundwater is the concentration in the sample above a certain threshold limit values. As I earlier said, the reference values are discussed before you go to the field, before you're going to send the samples to the lab, and then you know what the target values are. Incorrect sampling means incorrect analysis and incorrect conclusions. So we all know the expression, rubbish in, rubbish out, and that is also for the field work. So you have to be very careful in avoiding cross-contamination, being very correct with your administration during the field work to avoid mistakes. Because if you have a mistake, it will be carry on all the way to your remediation and can be very costly. So exact sampling is crucial. We have destructive sampling for offsite analysis. The sample is extracted from the media, and the media is soil or groundwater. The sample is packed and transported, and the sample is offsite analyzed. So that's destructive sample for offsite sampling, meaning you take the sample from the soil, you transport it, and then it's analyzed. Destructive sampling for on-site and or ex situ analysis. A sample is abstracted from the media, and the sample is on-site or ex situ analyzed. On-site and ex situ analyzed means that you have your equipment not in the lab, but in the field, and you can analyze your sample in the field. And non-destructive sampling for on-site in situ analysis. No sample is abstracted from media, and the characterized are established by remote sensing techniques. For instance, if you use a drone and you make an orthophoto map of your site, you can already identify spots where waste is being dumped, and that is remote sensing. Other on-site in situ analyses are, for instance, a penetration cone being brought down in the soil, and then the resistance being measured. So you can measure the different soil types by a penetration cone. So these are on-site in situ analysis. Destructive soil and aquatic sampling for off-site analysis. Borehole specifications, location and installation techniques should be recorded on your borehole, on your bore log, Textures being identified, soil description and recording the methods, sensory observation and description and recording the methods, soil sampling technique, aquatic. So you need to know the soil sampling technique, the aquatic sediments sample specification and location, the technique for sampling bottom sediments, also aquatic sediments, also called bottom sediment, the packaging and the preservation of the sample. Here we use cardboard boxes, and these cardboard boxes are filled with glass jars, and these glass jars were obtained from the laboratory because they needed this quantity of soil material to be analyzed. These boxes are then transported on a cold chain to the lab. So packaging and the preservation of sample you need to know before you start your work. The health and safety and environmental rules. On site you may have rules for health and safety. It's very common that if you go to a refinery, you have to stick to the rules of the refinery. Another aspect which you have to know is cross-contamination prevention method. How to prevent cross-contamination. Cross-contamination means that you are taking one sample which is contaminated and you would have another sample, and then traces of the other sample are brought to the new sample, and then your analysis is not correct because it's influenced. That counts for soil and groundwater. And you have to know the decontamination technique. So what technique will I use to decontaminate my sampling equipment before I move from one place to the other place? And then earlier discussed, the sampling, coding and labeling methods. Is also important to make agreements before you go to the field. What is my sample code and what numbering do I use? Soil samples have a different coding than groundwater samples and sediment samples. Destructive groundwater sampling for offsite analysis. What do I need to know? Groundwater well specifications, location and installation techniques, groundwater description and recording methods, development and purge of well techniques and methods. Development and purge means if you have installed a well, the well water is contaminated by soil elements and from above and below. And here you see we are pumping here the well after installation, and we continue until the well is clean. The water here is collected and then being brought to the sewer. Now, groundwater sampling techniques you have to know to take the correct hoses and pump. This is a hand pump, and we can use a hand pump because the groundwater was within 5 meters. If groundwater is deeper than 5 to 6 meters, it's getting very difficult. If it's 7 meters, you need a submergible pump. Then the next one is the packaging. What do I use? Bottles, glass bottles, plastic bottles, PE bottles. And this gets nowadays important, especially when you have a groundwater contamination with PFAS, because all of many tubings and pumps may contain PFAS or PFOS, and then you get cross-contamination. Then you need to know the groundwater table measurement techniques and how to record. The measurement techniques and recording of the thickness of an LNAPL. I discussed that, the LNAPL. Light non-aqueous phase liquids, for instance the oil, the floating layer. You saw that in the cross-section this morning. The has A rules on sites, cross-contamination prevention measures, decontamination technique, and here again, systematic sampling for coding and labeling for the groundwater. Destructive soil gas sampling for off-site analysis. So you take away the soil gas and you can bring that to a Draker multi-testing tube, and then you can analyze it and see what is in the soil gas. Destructive soil gas sampling for on-site analysis. Here an example of MIP, membrane interface probe, or rapid optional screening tool, or ROST. This is a picture of the MIP. This is a cone being brought into the soil. Here is a tip with a sensor for conductivity measurements. Here is an opening, a membrane, where the volatile components are sucked into this tube. The tubing goes to the truck on site, and there you have a GCMS to measure the volatile components. So this is a MIP, and this is an on-site analysis. Non-destructive sampling for on-site analysis, area photo interpretation, and ground radar. And ground radar is limited for heavy textured soil. Then the penetration depth is a minimum. how to get the most representative sample, and therefore the most representative data. Here you see an example of a piston auger, and here it's more or less half understood, and you see clearly the different layers of your sediment layer. If you use a grab sample like this one, it's very difficult to see the difference. Here you get just a mixture. Water, try to avoid that you have water with a lot of sediments. So on-site filtering of the water to be sampled is one of the methods to get a representative soil groundwater sample. These are pictures of sampling equipment for soil sampling for non-volatile components. Manual. These are Gorg augers. I showed you earlier the example where we used it in Armenia for the landfill. So we hammer it down and then you get your profile in this Gorg. This is percussion. Here you can have a pneumatic hammer on top and you hammer it down. And here also smaller Gorg for soft soil. And here is your knife. You just press it down manually and you get the profile in this Gorg, and with your knife you can take it out. These are augers. The Edelman auger can be used for soft soil. Then you have sand augers used for sand. Here you see that the wings of the auger are more closely, so the sand stay better. Different types in diameter. Then here there's a debris auger. It's open. Here you can go through debris and to gravel. Riverside, this is in wet conditions of sandy soil. Different diameters. And here are others when it's difficult to get in through stones. So these are more or less the available types of auger on the market to do manual augering. These are the auger bits, and here on top of the handle, it's with a bayonet connector, and you can use extension rods. Manually, you can at a maximum go 5 meters deep in soft soil. Sampling of non-cohesive soil or sediments below groundwater. You have different types, coring tubes and piston. This is a piston. Here is the outer tube, and inside you have the piston, and here's the ring, and you bring your piston on the bottom of your, on the top of your layer you want to sample. You pull this up with a rope, and you bring at the same speed as you pull this ring up, you bring manually down the auger, and in this way this piston fills with sediment, and when you take it out, you keep the piston at the height, at the last height, then you bring it to the surface, and then you press this down, and then the profile is being laid on the side above. Now this is in the same type, but then it's closed with a valve down here. And in cohesive below groundwater, you can use these Edelman augers, which I just showed you in the picture before. Many errors by borehole installation, profile description, and soil sampling are taking place. And I just have listed here a few. Incorrect interpretation of soil horizons, incorrect depth determination, you do not describe missing soil profiles, loss of volatile compounds from samples. If you are doing a survey for volatile components and you leave your sample on the surface when the sun is shining very hard, then you will of course lose your volatile components. And here also smaller Gorg for soft soil, and here is your knife. You just press it down manually and you get the profile in this Gorg, and with your knife you can take it out. These are augers. The Edelman auger can be used for soft soil. Then you have sand augers used for sand. Here you see that the wings of the auger are more closely, so the sand stay better. Different types in diameter. Then here there's a debris auger. It's open. Here you can go through debris and to gravel. Riverside, this is in wet conditions of sandy soil, different diameters. And here are others when it's difficult to get in through stones. So these are more or less the available types of auger on the market to do manual augering. These are the auger bits, and here on top of the handle, it's with a bayonet connector, and you can use extension rods. Manually, you can at the maximum go 5 meters deep in soft soil. Sampling of non-cohesive soil or sediments below groundwater. You have different types, coring tubes and piston. This is a piston. Here is the outer tube, and inside you have the piston, and here's the ring, and you bring your piston on the bottom of your, on the top of your layer you want to sample. You pull this up with a rope, and you bring at the same speed as you pull this ring up, you bring manually down the auger, and in this way this piston fills with sediment, and when you take it out, you keep the piston at the height, at the last height, then you bring it to the surface, and then you press this down, and then the profile is being laid on the side above. Now this is in the same type, but then it's closed with a valve down here. And in cohesive below groundwater, you can use these Edelman augers, which I just showed you in the picture before. Many errors by borehole installation, profile description, and soil sampling are taking place. And I just have listed here a few. Incorrect interpretation of soil horizons, incorrect depth determination, you do not describe missing soil profiles, loss of volatile compounds from samples. If you are doing a survey for volatile components and you leave your sample on the surface when the sun is shining very hard, then you will of course lose your volatile components. So if volatile components has to be analyzed, you take your sample and put it directly into your bottle or into your jar. And of course, you fill the jar and bottle completely with no headspace, because if you have headspace, your components can be evaporated. Now, cross-contamination, I discussed already, is a very common mistake in your soil survey. Mixing up soil types during drilling sampling, yes. Not using standard bore logs. You just take a piece of paper and you write down, then you will forget to write every information needed. Loss of sample, you have taken a sample, but it's not well maintained of it, just lost. Incorrect sampling labeling often happens. Incorrect recording, so you give it a number, but your record is wrong on the bore log. And not maintaining a cold chain. So these are just a few examples of errors during a fieldwork. Cross-contamination can be caused. Cross-contamination is so that you have a sample and it's being influenced by other samples that are contaminated. So these samples are not anymore representative. Smearing of soil during drilling. Yes, you go through a contaminated layer and you enter into a clean layer, but your bore bit is not clean, and you take contaminated parts from your contaminated soil horizon to clean horizon. That's called smearing. Contaminated material from above falls into your borehole. From above you have your borehole and you just stand around and you push by your feet soil particles from above into your borehole. You take your sample and then you have sample material from the above. Contact of soil sample and or drilling equipment with contaminated soil surface and contaminated standing water. So your sample equipment is coming into contact with contaminated soil before you're taking the soil sample, or with standing water. You just put your equipment on the soil and there's standing water which is contaminated, so it gets contaminated. Use contaminated sampling containers. Your sampling container is not completely clean. Use of contaminated drilling equipment and sampling material, and insufficient clean state of the drilling equipment. These are all causes of cross-contamination, and if you have cross-contamination, you do not have a representative soil sample. I told you now the ways of cross-contamination, but this can be prevented. 1. Sample on soil surveys, always use clean plastic foil. So on this picture, when you take a sample, use clean foil to put your sample here and not on the surface, because that surface may be contaminated and then you have cross-contamination. To prevent cross-contamination, all drilling equipment is proper and clean. All sampling material is proper and clean. So meaning that your jars, your tubes should all be clean. Decontaminate equipment before every sample. So you clean your equipment between every sample. The cuttings, this one here, are positioned in a sequence taken from the borehole. So don't mix it, but use a certain sequence to put the borehole cuttings. And implement and enforce health and safety environment zoning. And I'll come to that. This is the HSE zoning of a borehole location. This is my borehole. This is my truck with all my fieldwork equipment. This is the wind direction. And this is my foil. And here is a bucket to clean. This is called the contaminated zone. And this is called the decontaminated zone. Now you start with the drilling. So this is your borehole. You take your sample. You put it here. Sample number 2, sample number 3, 4, 5, 6, 7, 8, 9, 10. Make sure that this one is separate from this one, so that no soil particles are being spilled on one another. So you travel with your auger, put here 1, 2, 3, and here you start again. 1 of 6, 7, 8, 9. In this way, this one is not anymore disturbed if you are with sample number 10 or even sample number 20 or whatever. So from top to bottom, from left to, and when you're done and you with the sampling, you cover it with the liner, and then you start describing your profile and taking your samples. Prevention. Prevent contamination of deeper soil layers by loss of contaminated material in the borehole. By loose contaminated material in the air. Drill with a larger diameter to below the contaminated layer and continue with a smaller diameters, or use a lost casing. So this is, here you have your contaminated layer, and these are soil particles. You start drilling and they fall. The next sample will take this up, and then you get a wrong impression if you analyze it, because you detect these contaminated parts. How to prevent that is by a larger diameter drill passing this contaminated layer. That's why I showed you the different diameters of auger material. But you can also go to the last part, which is the most safe part. You drill through the contaminated layer, you introduce a plastic tubing and continue. And in this way you prevent soil particles to go or to move to this part which has to be sampled. Is that clear? So these are there's 2 manners to avoid this. Now this table is also given in the module, and here you see the auger types to be used in a different depth, and these are hand operated. So bedrock you cannot do hand operated. In clay, Edelman can be used until a maximum of 8 meters. It's quite, you have to be strong. Piston can be used in clay, and gorg auger can be used in clay. Sand, Edelman, you saw the Edelman with the rings very close to each other. Below the groundwater you can use a baler. Piston, This is sand. Sand is loose. And gorgs, you can also, this is plus or minus. Coarse, stones and gravel, difficult. Rubble, very difficult with hand augering. So we'll not start with that. Then you have to deploy different materials. And samples here. This one is disturbed. This Edelman auger is always disturbed. A baler is always disturbed. I should have a plus here. The piston is disturbed and gorg. And here, piston can also be undisturbed and undisturbed. So this gives you a brief overview of the different hand auger systems. Now we come to the machine operated soil and aquatic sediment. Hollow stem auger, maximum depth 40 meters, not in bedrock, peat. Below and above. Below is plus or minus, no gravel, rubble is difficult. It's undisturbed. A hollow stem auger, you can take undisturbed samples. Solid stem, again, 40 meters maximum, peat, above plus or minus, below not. Gravel not, rubble possibly, it's always disturbed. Percussion, so hammering down, maximum 8 meters, in clay and in peat, not in sandy soils. Gravel and stone is possible, undisturbed is also possible. Tricon, more than 100 meters deep, and here gravel and stones and bedrock. Tricon is with rotating rings with hard metal bits and teeth. Rotary coring, it's also possible. Baler, up to 150 meters, and for sandy soils and disturbed sampling. This is an overview of the mechanical operated soil and aquatic sediment sampling methods. You can consult this table in the guidance. Undisturbed sampling in boreholes. Baler with casing allow tube sampling. So the baler you cannot take undisturbed sample, but if you use a baler, you can go inside the borehole you made with the baler, and then the borehole is cased, and then that allow you for tube sampling. Hollow stem auger allow you for split pruning sampling. Solid stem auger with casing allow you also for tubing sampling. And why I have this list? That means because if you are able to take undisturbed samples, you have a very good representative soil sample of your soil. Okay, and this is a coring set. I just show you here this manual. So you make a borehole, you bring down a tube, you hammer it down. This is the tube. Then these are used to remove or to fill the headspace. You cap it and then you bring it to the lab. So here is the device to add this tube, and this one is the same distance as this one to avoid headspace, and this is the cap under, and this can be done manually. This is a small coring set, and here this is used for volatile components. You take your auger directly, take it from the borehole, you push this, actually the same system, a ring inside the tip of the auger, because this tip is the most undisturbed part of your auger. You take it off, you put it in your bag. Oh no, this is clean, sorry, this is the sample container being cleaned. Here it's put into the jar, and then the jar is being brought to the lab. This is for manual augering, for sampling volatile components. But you can also do the extraction of methanol in the field for volatile components, to sample volatile substances in the field. A bottle is filled with methanol and soil sample. Volatile substance will dissolve in the methanol on-site extraction. And then this is brought to the lab, and the lab is analyzing not the soil sample, but the extraction. This is good for volatile components. We discussed earlier the sensory observation, and we discussed the oil water detection. Now this is a sample tray, and here you can put a layer of water, You drop down a piece of the same dimension and you see what film is taken to the surface. And you describe the film with plus or minus or a large or small, but you take a consistent description. And then with this simple test, you can already tell what the potential concentrations are of your concentration with oil. So this gives an indication, and you record that on your bore log. Oil detection pen. I continue? Yeah. In the field, you have to describe your texture. And this is the texture triangle. And the texture triangle gives the percentage of clay here on this line, the percentage of silt, and the percentage of sand. And wait, there's something wrong in what's happening. Okay. By assessing the percentage of sand, clay, and silt, you can already in the field determine what we have. So clay, 60% of clay can have this percentage of sand and this percentage of silt. This needs exercise, but you can, by feeling, get this texture. Here's the sand ruler. It's also good to give the diameter of the sand. You put your sand sample here and you look which is the size of your grain size. It's called a sand ruler. And here are the fractions. Clay is from 0 to 2 μ. Silt fraction is from 2 to 36. Sand fraction is from 36 to 2000. Gravel is from 2000 to 63,000. And then stone fraction is larger. And this can be done by a trained person. Okay, I will continue. We discussed this, the bore log. I will not go into more details. Now we come to the monitoring. The purpose of monitoring installation and groundwater sampling groundwater sampling are taken from monitoring wells which are purged before sampling. Purged, cleaned, developed. During purging, field measurements of sampled water are taken, and then we measure the pH, electric conductivity, the oxygen demand, and durability. What is a representative groundwater sample, and what is the role of the field equipment in these? That's a question to be discussed, but representative will say that the pH is constant, the electric conductivity is constant, and that your sample is taken in a slow rate so that it doesn't move too much into your bottle to avoid volatile components to be evaporated. Now this is a wellhead, and here you see many wells inside, and this is also a wellhead but then under the surface. It's called a street box. Purpose of monitoring well installation: for sampling and analysis of groundwater samples, detect and measure D NAPLs and L NAPLs, dus the dense non-aqueous phase liquid, which is the heavier than water and sinks on aquitine, and the L NAPLs, the one lighter than water and floats. So also to detect these, you can install wells. And of course, groundwater level survey for hydrological studies. Now here is your floating cell, and here's your conductivity and your pH measurement. Here's the well. Here with the slow speed you fill your bottle, and that is the plume you want to discover by installing wells at different distances from the source. How does it look like, a well? So the material, be aware that if you have a survey for oil and gas sites, you cannot use PVC material because PVC material will soften in mineral oil components. This, what you do is you always try to use HDPE filter materials and a casing of also HDPE filter materials when you install. In this case, we choose for a diameter of 63 millimeters. The slots of the filter is 0.3 millimeters. The nylon socks around the filter here, sediments to go in, your label. Here, there is a label here, project number, project code, date of installation, well depths, filter depths, and the name of the installer. And this is how it looks like. A wellhead nicely protected with a lock, concrete covered to make it more stable. Now this will not be the case in your case, a frost line, but in our case, in our country, we need that. And then here, bentonite to close down. And this is the filter with the filter pack. This how it looks, this how the installation of a well looks like. This is another picture. The street box, the cover, the cap. This cap should be ventilated so that the water can freely go up and down. PVC of HDPE, I prefer HDPE. This is the Venus zone, yeah, above the groundwater. This is below the groundwater. And here you have your seal preventing this water to enter, but that the water comes from this part, the gravel, and your filter. Other wells, street box. And this well is crossing the groundwater table. And here you can detect your LNAPL. Dus if you want to detect an LNAPL, your floating layer, your filter should cross the groundwater table layer. If you want to detect the groundwater table above an aquitar, also called purged water table, you install your well on top of this aquitar. And if you want to get the groundwater of the aquifer below, you pass this part, you install a bentonite stop to prevent the top water to enter, so you're sure you take the water from this aquifer. These are two wells, one to get this purge water table and the other one to get the aquifer of the phreatic water. But you can also install it in one borehole, but then the diameter should be bigger and you have to install here 2 seals. The rule is that the one deeper is lower, so the height from surface is lower, and the one shallower is standing out a bit. And here you see this line is illustrating the ventilation cap. So there should be always a ventilation hole in the cap to prevent of the pressure to be built up in this pipe. While you install the observation, prevent cross-contamination, repair impermeable layers in the borehole by installing borehole plugs, by installing bentonite plugs, pump the well clean after construction by pumping groundwater at least 3 times the volume of the borehole. So if you have installed, you have to clean your well. So if you install a well and you want to clean them, you have to pump at least the volume equal to 3 times the volume of the borehole. So not the tubing, but the borehole itself. To be sure that you get the correct water, so the water from the soil around. When an LNAPL, a floating layer, is present and the groundwater has to be sampled, a lost casing has to be used. So you have to install a lost casing to prevent the pure material, the floating layer, to come into your well. And when a floating layer needs to be measured, the filter screen has to cross the groundwater table. I discussed that already. Okay, soil and groundwater equipment. When you do the sampling, you have to wait at least 1 week after installation before you sample to get a representative soil sample. Use clean materials such as pump, tubing and flow cell. So all the material to be used to sample should be clean. Use new materials such as hoses and sampling bottles. So also the hose in the well should be new and not, let's say, the old hose which was used for the cleaning of the well. Or let's say if you do sequences sampling, and you have sampled your well last month and you go back, you have to use a new hose. Purge monitoring wells until the electric conductivity and the concentration of oxygen are constant. Measure the turbidity. Label the bottles correct. Take the samples. Samples taken for heavy metals should be filtered on site, and the filter size is 0.5 microns. But samples taken for volatile and non-volatile parameters should not be filtered. because that will influence the quality. Use conservation liquids when necessary. Fill bottles without headspace and transport your sample bottles under a cold chain. Hand-driven pumps and electrical pumps. Hand-driven, then this is operated manually, but you can also have them motorized. And these are peristaltic pumps. Maximum depth is 8 meters. These are submergible small pumps, maximum 31 meters. You can put them in line, so in series. So you take one sample, you take 10 meters, you another pump in it, and so you can travel your sample to the service. But also you have, of course, the larger submergible pumps, but then your borehole and your well should have the diameter that can be, that when it should have the diameter large enough to fit this submergible pump inside. And this submergible pump is, of course, clean before you start using it. So it should be rinsed with clean water. Multimeters, I told you to do several, let's say, measurements on site before sampling. So you have different multimeters, and this is the flow cell. So the water from the well is coming inside, being measured, and then taken here to the sampling device to measure your floating layer. This is an acoustic sound, and it gives a signal when it passes through oil, and it gives a signal when it passes through water. So in this way, this is a measuring tape. So in this way, you can measure the depths of the L nipple, the floating layer, and the D nipple, or the layer which is consisting of heavier materials and are on the top of an aquitar. This is the turbidity meter. It's the same device, but here, this one, but then only for the water level. So it makes an acoustic sound when it passes the water. So then you know exactly the depth of the groundwater in the well. And here it's the groundwater N product. And this is the filter. The filter to be used when you are sampling water for heavy metals. You have to take out all the soil particles with this 0.45 micron filter, which is disposable. So you can only use it once. Now we come to sediment sample, core sampling, with or without piston, grab sampling, and disturbed or undisturbed sampling. This is taken, these are undisturbed samples taken with the device, which is not on the picture, but this is in a piston sampling or core sampling here. The grab sample, disturbed, free fall core sample, undisturbed. Aha, and this is the material here. From this sample, you get this one. Is this one. This is how it operates. You bring it down, you open the valve, you bring it down to the depth you want, then you close the valve, and then you pull it up. And here you see the line. And this is a multi-sample. It's more simple, but it's a tubing, and you just press it down. And here is a valve you operate. This is all for sediment sampling. Gas sampling, O2, oxygen, methane, and this is an installation. This is a gas sampling on a landfill. You bring down a hollow pipe and you attach that to a pump and your measuring device. And then you get an idea of the gas forming in a landfill. Wrong sampling analysis means wrong conclusions. A sample should be representative, rubbish in, rubbish out. Know what you and how you measure. It's important. This was it on the equipment to be used for sampling. Any questions? If not, I will change to my next presentation.
One question we have, Mr. Wood.
Yeah.
How can the recent recurring earthquakes and landslides affect sample collection?
Your conceptual site model should have the actual situation on site. And if there is a danger of flooding and landslides, that should be, of course, one of the risks. And if flooding or a landslide or earthquake happens, of course, your survey results are useless after the event. So unfortunately, when you are in such situation, you have to start all over again. And therefore, I mean, these are dramatic events, landslides, floodings, and so on. But also, just if you survey a site, often you come after 1 year and you want to proceed, people have starting to build or to dig or whatever. So your survey has an expiring date. And therefore, I earlier said that you have to allocate already your budget for your remediation before you proceed to your detailed site investigation, because detailed site investigation involves a lot of investment. And when you carry out a detailed site investigation and you leave the results for 2-3 years on the table, the situation may have changed dramatically. And then you have to start all over again. So if you decide to continue with a detailed site investigation, you also have to decide to continue with the remediation, and to do that just as quickly as possible after you have reported the site, to prevent that if you come back after 2-3 years, the situation has dramatically changed. So by flooding or by human activities or by fire or whatever. Does that more or less answer the question?
I think the answer is yes.